Welcome to this explainer. Look, if you're writing CUDA or working with GPUs, you need a mental model that bridges your software extractions directly to the underlying hardware architecture. No guessing. That's exactly what we're going to build today.
Think about it. How does a single kernel launch seamlessly control thousands of microscopic physical cores? To write truly high-performance code, we really need to know what's happening down at the silicon level.
Here is the roadmap for today. We're going top-down, starting with the overall GPU execution hierarchy, moving through software grids and blocks, down into the hardware streaming multiprocessors, then hitting warps, looking inside the SM partitions, and finally, putting the complete mental model together.
All right, part 1, the GPU execution hierarchy, bridging code and silicon.
We're basically operating in two parallel worlds here. In your software view, you're writing code that specifies a grid, which contains blocks, which then contain threads. Pretty standard, right? But the hardware, it sees something totally different. The hardware actually executes that work using the physical GPU chip, streaming multiprocessors, SM partitions, and actual cores. Our job is to map the first to the second.
Moving on to part 2, software grids and blocks, what we'll call the programmer's canvas.
So what's a grid? Well, it represents the entire wave of work for one single kernel launch. When you invoke a kernel from your host code, you are defining this grid. It's basically your ordered set of blocks processing your data. Simply put, one kernel launch equals exactly one grid.
Now, inside that grid, your threads are grouped into thread blocks. And there's a good reason for this grouping. Threads inside the same block are specifically designed to cooperate. They can sync up their execution using commands like sync threads, and they can rapidly share data using super-fast on-chip shared memory. To put that into perspective, let's say you're doing a 1D vector addition on 1,000,000 elements, and you assign 256 threads per block. Your single grid will automatically launch roughly 3,907 blocks to cover that whole dataset. It scales up fast.
But here's the crucial point. You define these blocks in your code, right? But you don't assign them to specific physical locations. You can't just tell block 0 to go sit in the top left corner of the chip. So how do these software blocks actually map to the physical silicon? Well, the hardware steps in and handles that entirely behind the scenes.
Which brings us to section 3, hardware, streaming multiprocessors, or as I like to think of them, the mini GPU factories.
Meet the true workhorse of the GPU architecture, the streaming multiprocessor, or SM. Think of each SM as a highly autonomous mini GPU factory. A modern GPU chip is packed with these, and each one is fully loaded. It owns its own register files, its own shared memory, its own schedulers, and its own execution cores, the whole shebang.
So let's trace the exact lifecycle of how your blocks get dispatched to these factories. Step 1, the driver enqueues your grid. Step 2, the GPU hardware sets up a global pool containing all those blocks you just launched. Step 3, as the individual SMs find available capacity based on their register and memory limits, they actively request blocks from this pool. And Step 4, this is absolutely vital to remember. Once a block is assigned to an SM, it stays on that single SM for its entire lifetime. It literally never migrates.
All right, section 4, warps, the real execution unit, executing in lockstep.
Let's zoom inside the SM now. The threads of your blocks don't just run wildly. They are automatically grouped into fixed execution sizes. And that magic number, for all NVIDIA hardware, is exactly 32 threads. This group of 32 threads, that is what we call a warp. And honestly, the warp is the true unit that the hardware scheduler actually manages. The threads inside a warp execute together, in perfect lockstep, using a paradigm known as single instruction, multiple threads, or SIMPT. Practically, this means if you define a block of 256 threads in your code, the hardware seamlessly slices it up into 8 distinct warps. It doesn't schedule 256 independent threads, it schedules 8 warps.
Section 5. Inside the SM partitions, microarchitecture at work.
Zooming in one final time, let's look past the SM level and check out the microarchitectural subdivisions. Modern SMs, like the Ampere or Hopper architectures, they aren't just one monolithic block. They are internally divided into SM partitions. The warps assigned to an SM are distributed across these partitions, and each partition operates completely independently. Each one gets its very own warp scheduler and a dedicated subset of execution units, whether those are your standard CUDA cores for floating point math or tensor cores for AI workloads.
Here is how a single execution cycle plays out inside one of these partitions. Step 1. The partition's warp scheduler looks at its pool of assigned warps and grabs one that is ready, meaning it's not stalled waiting on a memory fetch. Step 2. The warp's instruction gets decoded. Step 3. All 32 threads in the warp load their respective data. And Step 4. The physical cores actually crunch the math. Now, if one warp stalls waiting for data, the scheduler instantly swaps it out and issues an instruction from a different, ready warp. This constant seamless interleaving is exactly how GPUs hide memory latency. It's brilliant.
Finally, Section 6. The complete mental model, putting it all together.
Let's pull back from the microscopic view and consolidate this into a single, comprehensive mental map. This mapping is absolutely crucial for your day-to-day work. Let's recap. Your grid maps to the entire GPU device. Your thread block maps entirely to a single streaming multiprocessor. The internal SM partition, with its warp scheduler, well, you don't see that in your code, but it's the engine of hardware efficiency. The warp of 32 threads is the actual scheduled unit. And finally, your individual thread maps right down to operations on the physical CUDA or tensor cores. You write the abstract code, the hardware physically runs SMs, partitions, warps, and cores.
So why does this matter? By understanding this exact hierarchy, you can drastically tune your applications for maximum performance. You choose your block size, say 128 or 256 threads, to fully utilize the SM's resources. Your ultimate goal here is high occupancy. You want as many active warps residing on the SM as possible at any given time, because more resident warps give those internal schedulers plenty of choices to hide memory latency. Just keep in mind, if you use too many registers or too much shared memory per block, you'll hit hard hardware limits, like a maximum of 64 warps or 2048 threads per SM, and that immediately chokes your occupancy. The hardware automatically handles the lower-level scheduling, sure, but you have to supply it with the right shape of work.
Which leaves us with a critical question to close out on. The next time you sit down to write a kernel, are your software abstractions fully feeding the hardware factories beneath them? Keep this architectural map locked in your head, and you won't just be writing code. You will be expertly orchestrating high-performance silicon. Thanks for joining me for this explainer.